Thank you everyone. It's lovely to be back here at .NET London. This is my second time with this meetup. I'm from Australia, as you might be able to tell from the accent. And as Dylan said, I've been living in France for the last year, but 3 years ago I was in London as well and came and gave a demo of some F# code, which I now understand was a very brave thing to do. But if you remember that, thank you. But yeah, tonight here I'm here to talk about streams and queues. And we'll get into what they are and why you might care about them if you're not sure about that yet. But the title of this talk, yeah, it's like 10,000 streams when what you need is a queue. And I've done this talk in a few different places, and I have to check who actually recognizes the reference here. Not everybody. This is interesting. So I'm just checking, is it the grey hair or is it the English Cultural Association? I don't know, because in Copenhagen hardly anybody knew about it. In Antwerp, not so many as well. I thought it would be more here, actually. But if you're not sure what it is, scan this QR code because it will take you to YouTube. And don't hit play straight away, but save it for later, because later tonight you'll get to enjoy. I'm just waiting while a few people scan. We can play it in the pub, exactly. You will get to listen to the absolutely iconic sounds of, waiting for the last phone to go down, Alanis Morissette singing Ironic in 1996. And she regales us with a whole bunch of examples of things that she finds ironic as she cruises around Canada with 4 clones of herself in different coloured tops, sort of laughing and joking around and singing about ironic things. If you remember 1996, which some people seem to do, you might remember there was some fierce debate over how ironic these things actually were. Because many people were like, that's not irony, that's just unfortunate. I used to be team not irony. I've changed my mind. I now think Alanis understands irony better than any of us, and we can get into that at the pub too if you want to. So an example of a few things Alanis finds ironic. It's like black fly in your Chardonnay. It's a traffic jam when you're already late. Or it's like 10,000 spoons when all you need is a knife, which is obviously the inspiration for my talk title, It's like 10,000 streams when all you need is a queue.
Is that AI?
This is not AI. This is my completely clumsy copy-paste job. So why are we talking about streams and queues? It's all about event-driven architecture. Who is doing event-driven architecture in their workplaces? Yeah, quite a few people. Who has been told they should do event-driven architecture but isn't sure if they actually are? Yeah, a couple of Who's been told to do it and just refuses to? Was that where you were going?
I've told people to do it, and then I learned what it was.
And then you learned what it was.
That was a long time ago.
Excellent. So event-driven architecture, it's this whole approach to systems design that orients the design of the system around events. So what are events? We call these things domain events. They represent things that happen in your business domain. So it might be something like, we usually express it as noun-verbed. So the thing that something happens to, and then the thing that happened to it, but expressed in the past tense. There's good reasons for expressing it in the past tense. An event represents a fact about the world, something that has happened. So we're describing an event that has occurred. It's in the past, so we say noun verb. So it might be order submitted, user registered. There's the thing that you'll notice here is one of the nice things about event-driven architecture is it guides us to use the language of the domain. We don't say user created, we say user registered. So it encourages us to think about the verb that actually has some meaning to the people in our business. People that use terms like user created or user updated are thinking about the database. They're not thinking about the company or the business operations. So when we're doing event-driven architecture, we're trying to think about what is actually happening, not just the things that they happen to, but what is happening to them. And we think about them in the past tense because it allows us to think about the sequence of events. When do they happen relative to each other? There's also these blue stickies, so the events were all orange stickies. Blue stickies represent commands, which is like the inverse of an event. It's what you want to have happen. So it's like a statement of intent. Submit order, order submitted. You often find, if you're doing event-driven architecture, you find these pairs. I want this thing to happen, and then at some point, if everything goes well, it has happened. So we've got time as part of the flow of our system. One of the best ways I think of to discover the events in your business domain is a practice called event storming. If you're doing event-driven architecture, did you do an event storm? Did anyone do any event storming? Has anyone heard of event storming? Yeah, a couple of hands. So this talk is not about event storming. It's a great technique though. So if you're curious about it, do Google it. It's a really great way to get a whole bunch of people together, people from all across your business, salespeople, customer service people, product owners and engineers, to sit in a room with a big long wall of butcher's paper, and you give everyone orange sticky notes and you ask them to write what they think happens in your business and stick it up there. There's a whole process that helps you sort of refine it down to a coherent and shared understanding of what actually happens in your business. And so you might end up with something like this. So this represents the output of an event storm of a typical sort of e-commerce site. So you've got commands like register user, and then the user becomes registered. Then they're going to add items to cart or remove them from the cart, and then the event is item added to cart, item removed for cart, submit the order submitted, and then a bunch of events that don't really have commands associated with them because they just kind of flow through. So like payment successful or payment failed, then the order is considered accepted, then shipped and received. So it's kind of the time series. If you remember back to the old way of doing sort of data modeling or domain modeling, it was a very static view of the world. We sort of came up with the nouns. You remember that? Find the nouns? You remember being told that for object-oriented design? Find the nouns. Event storming and event-driven architecture adds time to the dimension. So it's not just about what the things happen to, but what actually happens to them. And we represent it from left to right in the flow of time. The nice thing about this is it allows us to start to think about different parts of the workflow. We can think about different subdomains, or as we call them in the field of domain-driven design, bounded contexts, because they represent boundaries around different subsets of the workflow of the business process that we can think about independently. And probably we're going to be changing them independently as well. So if we've isolated the whole way that we do payments, maybe today we accept credit cards, tomorrow we need to accept Bitcoin, the next day we need to accept some sort of weird agent token-based payment system. It's sort of encapsulated and isolated and won't affect the shopping cart or the shipping system. So we're looking for modularity and decomposition of our system based around the actual stuff that happens in our business process. So it's nice. You can do the event storm out there and you kind of find these boundaries. It's a really helpful way of both coming up with a system architecture and understanding the flow of activities through your business. Once you have these bounded contexts, you can actually start to think about the events not just as things that happen in the business, but as mechanisms of communication between the bounded contexts. When we do the event storm, the orange sticky note on the wall is just someone saying this is a thing that happens. But at some point when we break our system up into different parts, that thing that represents a thing that has happened is probably also going to become a piece of information that we want to flow between the parts of our system. So in this case, maybe we're publishing an event which can go to multiple subscribers. So in this case, our shopping cart is publishing an event that's going to the payments and the shipping subscriber. Or maybe we have a command that is offered out there and multiple senders can send that command in. This is the interesting thing about commands and events once you start thinking about the flow of information between different parts of your system. It's about the directionality of coupling. A lot of people say, oh, we're going to do event-driven architecture because it's more loosely coupled. That is, unfortunately, I'm sorry to say, not the case. It just inverts the direction of the coupling. So if you have systems that feel tightly coupled, inverting the direction may make them feel less tightly coupled, but the coupling is still there. It's just in the opposite direction. So in this case, the publisher is not coupled to its subscribers. You can come along later and add more subscribers without changing the publisher. Not a problem. With a command, you can come along and add more senders without changing the handler, right? But it's the directionality compared to the flow of information. I'm seeing a few people going like, sorry, what? So maybe just sit with that for a bit. If I said we've got an event now, let's get into the implementation of the system. Who immediately jumps and says, oh, that's going to be a Kafka topic in my Kafka cluster? Yep. Somebody's like straight up there? Yep. Not everybody though. Who thinks of it as like a queue and a queue-based pub sub type system? Yeah, a couple of hands going up. And who thinks of it about event sourcing and event stores? Yeah, a couple of hands. The reason I made this talk is because these three things are very different. They're very different technologies. They're very different ways of representing an event in your system. And what I hope to do is guide you through some thinking around like how to decide which event should actually flow into which one of these implementation technologies. Because the thing is, we often, I think, in systems design, a lot of people these days, we're just so focused on the code and the runtime. But there's this concept, goes back to the 90s as well, much like Alanis, called Christian's 4+1 views. And I found this so valuable in thinking about systems design and architecture. What it encourages you to do is to look at the system from multiple perspectives. You've got your logical view, which is your business concepts, those elements of the business domain, your entities and your events. You've got the process view, which is the runtime processes, so the actual executable bits of software that are running in production. You've got the physical view, which is the infrastructure that they sit on. And then you've got the development view, which is your source code layout, your modules and packages and repositories and folders and disk structures and so on. These are all the same system, just different ways of looking at it. And a lot of people, when I say draw me the architecture of your system, they will only be able to draw you either the physical view or the process view. Yeah, seeing some nodding heads there, right? If I say draw me the architecture, who will just go and say, oh, well, we've got a load balance and then we've got a cluster of servers here and a database, right? That is one view of your architecture, it's not your whole architecture. If you're ignoring the logical view, you're forgetting the actual architecture of your business and how that maps onto the elements of your system that are going to be running. And so when we're talking about event-driven architecture, and in particular the focus of this talk, I'm really going to focus in on the logical view and the process view. The order submitted orange sticky note is in the logical view. It's a logical concept. When you identify it through your event storming, it doesn't tell you anything about how it's going to manifest in reality, in your code or in your runtime. But things like Kafka topics and queues and event stores, they are part of your runtime. They're the elements that are going to exist in production. So what we're going to look at is how do we map between these logical views and process views. But to decide, we need to really get into understanding the difference between these technologies. So a big chunk of this talk, sorry, I'll go back here, is talking about the difference between streaming topics like Kafka topics and queue-based pub-sub systems. And then later we'll look at event sourcing and event stores because they are a different beast altogether. So when I talk about queue-based pub-sub, I'm talking about RabbitMQ. Who's heard of Rabbit? A couple of people? Yeah, lots of people, cool. Or AWS SNS SQS or Azure Service Bus, they're very common systems. When I talk about Kafka streams, we're talking about Kafka or AWS Kinesis or Azure Event Hub. So all the major cloud players have got systems that represent these two patterns of representing events. Google PubSub is kind of a bit weird in that it tries to do both, and the success with which it does both will vary depending on who you talk to about that. So, but we're not really going to focus on that today. We'll start with looking at what do they have in common. So the first thing is that they're all considered message brokers. So message brokers is a generic term for anything that facilitates transferring a message from one system to another. When we talk about transferring the message, there's usually some concept of a topic. Looks different in different systems, and there's some concepts of storage, because if we're transferring a message from one system to another through a broker, the broker is going to store the message for at least some period of time until the receiver can pick it up. Right? So we've got topics which identify different collections of messages, and we've got the storage of those messages. So Kafka and queues, they both do that. They both have producers and consumers. So we talk about a producer being the thing that creates the message and pushes it into the broker, and the consumer is the thing that pulls the message out of the broker. It consumes the message. And so you can have producers and consumers with both types of systems. The interesting thing about the terminology of producer and consumer is that it's a very process view oriented terminology. It's about the production of the message and the consumption of the message. It doesn't tell you about what the message means. And you'll notice before that when I talked about commands and events, I used very precise terminology. I send commands and I handle them. I publish events and I subscribe to them. Right? So if I hear someone say, I'm publishing an event and I'm subscribing to it, they're thinking about the meaning of the event, the business meaning of it. If I hear someone talking about producing and consuming messages, they're not talking about the business meaning, they're just talking about data. So treating it as just random data that needs to get from here to there. It might seem like that doesn't matter, but it actually does. The distinction between these two things and how much you think about what do these flows represent in terms of your business system. Both kinds of things have the concept of delivery guarantees. This is a deeper topic we could get into, but I'm going to skip it for tonight. You've got these different kind of delivery guarantees, at most once. So you might drop a message. So you might have the message doesn't get there, but at most you'll at least get one time. You have exactly once, which is actually a little bit complicated because you've got all these different hands-off messages, so to actually do it, there's a bunch of other things that happen, but again, I can talk about that later if anyone's curious. And then you've got at least once, which is where one message might actually get sent through twice. This is actually the most reliable thing to do from the broker's perspective, because you never actually know if someone has actually received a message. So sending it more than once is the best way to guarantee it actually does get there in the end, but it does require the consumer to deduplicate that message. But anyway, so whichever system you're using, you have to think about, are we focused on at most once kind of scenarios, exactly once scenarios, or at least once scenarios? But that's all that they have in common for the most part. Now we're going to get into the deep differences, and there's 4 main areas of differences. We've got the message distribution. How do they actually decide how the message gets from one place to another? We've got consumer scale out. How do you decide when you've got consumers that are, where you want to scale it out horizontally, how do you manage that? It's different between the two systems. What happens when you have failures processing messages? Maybe the node goes offline or the process dies, or there's a message that just can't be processed. And then we've got differences between message routing, where we have to make different decisions around how the message gets, where it needs to go, one place or another. So we're going to we'll start with message distribution. What I mean by message distribution is answering this question: who decides if the payment service should receive a given message that has been produced by the shopping cart service? And queues and streams, they handle it. It's a very simple question. It seems quite obvious, but they handle it differently. And the difference is that it all comes down to the state of the message. For a given message, who keeps track of whether it has been read or not, whether it's been consumed or not? So with queues, it's handled in the broker. That's why I've put a little database in the broker there, but with streams, it's handled in the client. So let's look at what I actually mean by that. With a queue, the client is just saying to the queue, pop off the next message. Just give me the next thing you've got. I don't know anything else that's going on, but I just want the next thing. So that's a stateless operation. It doesn't need to know anything about the state of the queue or the state of any other messages. It can just say, give me the next one. But with a stream, when you talk to the broker, it has to say, I would like the next message after offset X. So it has to keep track of this offset X. That's the state. So I talk about these things as being stateless consumers or stateful consumers. And that's actually the fundamental difference between the two. Now, you don't really notice this when you're just using them, because a lot of the complexity of the fact that it's stateful is baked into the client libraries when you're using Kafka. But the consequences of it are things that you do need to understand. So let's look at some actual message flows. If on the queuing system, shopping cart's pushing into the queue and streams are appending into the log. So that's some new terminology for you. I called them streams before, but more precisely, they're called distributed logs. And when you push a message into the queue, what you're actually doing is appending it to the log. So we're appending that to the log or pushing it into the queue. Maybe we push a second message in, and then the consumer in the queue world, it says pop off the queue, and in the stream world, it says read from offset 0. And after having read it, and it's read offset message with ID 1, it updates that state storage to ID 1, right? So it's keeping track of the state of how much it's read so far, but the queue isn't. It's just saying, give me the next message. So maybe we get a third message coming in. We're still just saying pop off the queue, we get ID 2, but in the streaming world, we're saying read from offset 1. Because remember, it kept track of what message it was up to. So now it says read from offset 1, and it gets back ID 2, and it updates its offset. And then it says read from offset 2, and it gets back ID 3, and it updates its offset. So in the queue world, we're just doing the same thing over and over again, pop off the queue, pop off the queue. And in the stream world, we're reading from the offset that we remember. Now the truth is, to clarify, this is what I mean by the statefulness of it. So at the end of it, the queue is empty. The messages are gone. They've been read and deleted from the queue. So that's the state. The fact that it's empty now is it knows that if someone else says pop off the queue, it's going to say, I've got no more messages to give you. So the fact that it deletes those messages is the state management that we're talking about. But with the distributed log, it keeps the history of the messages. And that's why the clients need to ask for the specific offset that they want. Because if they said to the broker, give me your messages, it would always give all the messages. But you don't obviously want that. You only want the new messages. So you have to tell it, where do you want to start at? And people that mostly use queues are kind of shocked that this is how streams work, and people that mostly use streams are kind of shocked that that's how queues work. So this is why I draw that distinction. So we've got stateless consumers, because the queue's managing the state in the queue world, and we've got stateful consumers. Now, the reason that you don't really have to worry about this when you're just writing a simple client as the consumer is that it's handled by the client library. It actually stores that offset number back into Kafka for you in a special topic called consumer offsets. So the client library, so if you go, NuGet install kafka.client and you say consume messages and you get a message back, it will automatically write this into a topic in Kafka. But if you wanted to write your own Kafka client, you could store this offset in a separate database if you wanted to. The broker itself doesn't know that it's going on. The broker itself doesn't know that it's storing the offset that the clients are using to read the next message. So that's why I feel justified in saying that it is still a stateful consumer. So this leads us to one of the first ironies, because if you look at the flow of these messages, with the queue you've got messages flowing in and flowing out, and with the stream you've got messages going in and staying there. And when you look at Confluent's advertising for Kafka, they call it data in motion. And I have to say, I think that Alanis can help us out here. I think, because isn't it ironic? It's like your data staying still when you thought it was in motion. I never claimed to be a lyricist. So I told you she had different coloured tops on. This is the yellow one. So the first irony, I actually think Confluent advertising Kafka as data in motion is a bit of a misrepresentation, because I think queues actually have data in motion is a far more accurate metaphor for queuing systems, not streaming systems. All right, so that's message distribution. Let's talk about consumer scale out. What I mean by consumer scale out is when you've got multiple copies of the same consumer. So because queue consumers are stateless and stream consumers are stateful, this is quite important. Like we know about stateful and stateless scale out from the web world, right? Who remembers cookie-based session affinity? Sorry to bring up the PTSD of this world. If you don't remember this, in the bad old days, before the cloud, when we didn't have dynamic scaling, it wasn't uncommon to actually have web servers store state in memory. And that state would belong to a specific user. And so you'd have a cookie ID, and your load balancer would remember that that cookie ID needed to go to server A, and a different cookie ID needed to have its request go to server B, because if it went to the wrong server, the data wouldn't be in the memory, and everything would go badly. So luckily, at some point, we realized that's a terrible idea, and we externalized our state, and we went for state, like this is the whole thing with the cloud, right? We pushed for stateless web tier processes, because that allows us to scale out very easily, and the load balancer can send any request to any node, and we can quite much more easily balance it. When we had content-based routing through the load balancer, like session ID cookies and payload-aware hashes, we had to make sure it went to the right node. So if we added a new node, none of the existing users could get allocated to that. And if we deleted a node, all the existing users' sessions would disappear. You can see why we stopped doing this. Terrible idea. Oh, have we lost? No, we're back, sort of. Power saving, excellent. I love it, efficiency, it's great. Yeah, so I've been talking about stateless and stateful web servers. When we have stateless and stateful event-driven architecture consumers, the stateless world is more like a queue, the stateful world is more like a stream, because what it means is specific messages have to get processed by specific nodes. So when we talk about scaling out stateful clusters, we can refer back to other patterns that we've seen with stateful nodes scaling out. One of the most common is databases. So you often find sharding, where different nodes in your database cluster handle different subsets of the data, sharding or partitioning. We've got traffic type splitting, where we've got read nodes and write nodes. Might remember that from database world. And there's like workload allocation as well, where different nodes have different responsibilities. I did have someone call me to task on this, because I say that streams use these patterns. I want to be more precise. With the workload allocation, the nodes in a consumer cluster of Kafka, they don't talk to each other in the way that this diagram might misrepresent it. But they do have different roles allocated to them. Specifically, one of them is allocated the role of a leader. So I'll show you what that looks like. So let's say we've got two nodes in our payments cluster, and we have one message. With the queue, it's pretty straightforward. We pop off the queue, and only one of them gets the message, because the queue's keeping track of the state. So was the first one it gives it to, it says, all right, you've got it now, that message is done. The second one says, give me the message. It says, I got no messages for you. So the message only gets processed once. With the stream, if we don't manage it carefully, and if we didn't care about which node was handling which message, and both of those nodes were sharing the state, they would both say read from offset 0, they would both get back the message with offset 1, and they would potentially both process that message. So you get the message processed twice, which is typically not something you actually want when you're talking about something like order submitted and now you need to process a payment, right? You don't want it happening twice. So yeah, not so great to have it processed twice. In the queue world, we call this the competing consumer pattern, because the nodes are competing for the next message. They're like fighting each other. Give me the next message. No, give me the next message. But the queue broker decides, you're going to get the message, not you. But then the next one that comes in, I might give it to that one and not that one. So it's kind of load balancing between the consumers. With the streams, this just would never work. Now, this is called a low-level consumer of Kafka, and nobody actually ever uses this for obvious reasons. It would be a terrible idea. So what they actually do is they have a high-level consumer. And the high-level consumer keeps track of the offset separately, but it requires your distributed log, your Kafka system, to be partitioned. Remember I said before about we have sharding or partitioning, where we say some data goes on one node and other data goes on another node. So the way it works in Kafka is you partition it, and on your producer side, you'll have some algorithm to decide for a given message whether it ends up on one partition or another. Usually you key it off the ID of the entity that the message is related to. You don't have to, there are other ways to do it, but that's quite a common one. And then on the consumer side, you have this thing where the consumers are allocated to a partition. So one node is only reading from partition 1 and another node is only reading from partition 2. And so this is what I mean when I say they're stateful. They have to have the state and they need to be allocated to the partition, because otherwise they'd be reading they're reading the same message twice. But now we've split the messages up. Message 1 and 3 is on partition 1, message 2 is on partition 2. They've got different offset storages. So when node 1 says read from offset 1, it gets message 3, and when node 2 says read from offset 1, it gets message 2. So this is good, right? Now the message is only processed one time by a different node. If something goes wrong though, there's an interesting side effect of this. So let's push in a few more messages, message 4 and 5. If process 2, so if the second node dies for some reason, maybe Amazon decides to shut it down or Azure decides to shut it down, well, in the queue world, it'll just process all the messages. That first node will pick up the workload. It'll pop off the queue and get message 4, and then it'll pop off the queue and get message 5. But in the stream world, node 1 is only reading message 3 and then message 5, and message 4 is getting skipped, because that partition now doesn't have a node allocated to it. So this is why you have to be aware of this, because this is a thing that can happen and you need to know what's going to happen to your systems. So what actually happens though, remember I talked about different roles and responsibilities in the different nodes of the cluster. There's a node that's a leader and there's a group coordinator, which is actually running in the broker, and it will detect that a node has gone offline and say, oh, this is a problem. There's been like 3 or 4 seconds without any read operations. I'm going to reallocate this partition to a different node in the cluster. So each node can actually read from multiple partitions. And in this case now, eventually, there'll be some partition rebalancing and node 1 will start reading from the offset storage of the second partition, and it will pick up message 4 eventually. So you can kind of see here there's a lot more complexity going on in the Kafka world because of this partitioning and the fact that the clients need to be sort of partition aware. Whereas with the queue system, the clients, internally to the broker of the queue, there may well be partitioning going on, but the clients are agnostic to it. The broker's responsible for distributing the messages across its cluster and making sure that they come out to the nodes correctly. And this also, as you can imagine, affects elastic scaling, because if you add a third node to the elastic scaling cluster, you can immediately add to the processing capacity of the cluster in a queue world, because again, the queue is just going to start distributing the nodes out to the the messages out to the third node in the cluster. Whereas in the streaming world, if you've only got 2 partitions, but you've got 3 nodes, that third node's doing nothing. So this leads to a phenomenon where if you're using Kafka, you typically over-provision your partitions. You might say, well, we think we're probably going to scale up to maybe 20 nodes maximum, so we'll create 50 partitions. That gives us a lot of headroom. I have seen clients that I work with who underestimated that, and they get to a point where they actually want to have more consumers than they have partitions, and they have to go through a partition rebalancing process. Look, it's not the end of the world, but it's just something that you'd probably prefer not to have to do if you didn't have to. So, but you have to be aware that this is a risk that might happen. So, back to Alanis sharing her ironies with us, or me bastardizing them into terrible, non-rhyming verse. It's when you need to scale out, but your partition count's too low. I'm sure Alanis would have a lot to say about this topic. Is that a different coloured top? It is. Different coloured gloves too. She really goes to town with the colours in this video clip. It's fantastic. So, message processing failure. Let's say we've got a message and the message itself can't be read. So we looked at node failure before, which is where one of the nodes goes offline. Now we're going to look at where a specific message has an issue with it. So I'm going to push a couple of messages into our different systems. And then when the queue system pops off the queue, I did gloss over one detail before. I said that it just gets deleted from the queue. But actually there's a period of time where it's still in the queue, but it's marked as invisible. So while it's being processed, the queue still keeps a copy of the message, but it won't release it to anybody else. The specific mechanism varies depending on the queuing system that you're using, but they all have this kind of phenomenon. And what actually happens is eventually there'll be an explicit acknowledgement. In the streaming system though, the difference is that the offset is just not yet updated. So while you haven't yet successfully processed the message, you haven't updated the offset. If you do successfully process the message, then you acknowledge it back to the queue, which effectively deletes it. So it's like an explicit confirmation. This message is all good. You don't have to give it to anybody else. But with the distributed log, the way you do that is you commit the offset. And now you know that you've actually successfully processed that message. So if we try and read off the message 2, and let's say there's a failure, some deserialization error or some out of order processing that leads to a null reference exception, or some nonsense happens when we try and process this message and we actually fail to do so, then what will eventually happen in the queue world is that after some time it will say, well, they never acknowledged this message, so actually it clearly needs to get processed again. There's some differences again in the different systems. So like Amazon SNS, SQS will have like a timeout. RabbitMQ will actually wait until the node disconnects and assumes that the client has gone offline completely before it re-releases the message. But either way, at some point it will re-release the message for trying again. So we call this a retry process. In the queuing system, it's kind of tricky. So if the node itself fails and you haven't committed the offset, then when the replacement node spins up, it will start again from that same offset. Right? If the node doesn't fail, and if you just throw an exception and catch it and do nothing, then you'll just say, well, give me the next message. Even if you didn't commit the offset into the Kafka storage, the in-memory client will have kept track of it, and it will just get to the next message. So actually, the thing you'll observe if you don't do anything special, and if your node doesn't go offline, is you'll actually just skip the message by default. And I've had some Kafka people come to me and say, no, that's not by default. And when I talked to them about what they did, it turns out that it actually kind of was by default, but they were doing some other things to make sure it didn't happen. So one of the themes here you'll see is that I'm not saying that like you can't do the same things with queues and streams, but on some system, if you're using queue and you want to do some of the things that are easy with streams, you have to put a lot more effort into it, and vice versa with streams and queues. So it's not so much about what's possible, it's about how much effort is involved. And as we can see, when there's a failed message and you want to retry it, then with streams it's a lot more difficult. Some reasons why you might want to try it. Maybe your database was offline for just a fraction of a second, or there was a network congestion issue, or a third-party downstream system had a failure temporarily, or maybe you got a 429 error. We heard about that before. And so some sort of a system that's going to sort of automatically retry that for you in those cases, those temporary failures, is quite helpful. And with Kafka, it won't do it for you automatically. You have to put some thought into it. You have to either fine-tune the client library or find another library that will take care of this sort of retry process for you. There is a way to retry it, which is that you can explicitly tell the client library that you want to go back to a specific message ID. They call it a seek operation. Again, that's not something that you typically do manually. You rely on some sort of third-party library to take care of it for you. But with the queuing system, once that timeout happens, it'll re-release the message and it gets popped off again. And if it was a temporary intermittent failure, then everything's good and we can go about our day. And having worked with event-driven systems, particularly using queues, this is a fabulous feature, because these sorts of intermittent failures, where if you were directly doing the operation from a web request, would have led to a 500 straight to the user, it doesn't happen anymore. It gets caught, there's a retry, and eventually the thing happens, and customers are happy because the thing they wanted to happen does eventually happen. If there is a situation where it actually fails repeatedly, so maybe it's not a temporary failure, but it's a problem with the message that's never going to go away, so deserialization or some kind of actual bug that you've found, maybe you updated something on the consumer side or on the producer side and not the consumer, or vice versa, then eventually the queuing system will keep track of that, usually like a counter, and it'll say, okay, this message has failed like 20 times, I'm not going to keep re-releasing it, I'm going to put it into what's called a dead letter queue, a special place for poison messages. So you can monitor that queue, you can pull those messages out, inspect them, decide, do we want to reprocess them? Have we fixed the bug? Do we need to modify the data in the message and put a different, like slightly mutated copy of the message back into the queue? Your operational people or SRE people will have to decide what to do with that message. But the point is that we're really focused on, by default, making sure that every message eventually gets processed. And their tools are there to help you do that, even in the cases where it failed in unexpected ways. With the distributed log, there's really no kind of facility to help you with that. You have to make choices, you have to find libraries, you have to write your own kind of handling. Different strategies people have is that they'll have separate topics in Kafka for each topic that they've got, and they'll write some code to put copies into the separate thing, maybe for retries, maybe as a dead letter queue. There's a whole bunch of different ways, and not really any kind of universal standard for handling it, because it's not handled by the broker. Everybody sort of does it their own way. And if you don't do it right, you can end up with this phenomenon called head of line blocking. So if you don't handle it well, what can happen with the streaming world is you just get stuck processing this one poison message over and over again. You've said every message is important, so we're going to put in place a retry mechanism, but you don't think carefully enough about dead letter queues and like when do you stop retrying, and you can actually end up in a situation where like that message at the head of the line is blocking all of the other messages, which is obviously not a good thing to have happen. So Alanis comes to the rescue again with one more irony for us, which is a new dev team adopted EDA, got head of line blocking on their very first day. Isn't it ironic? Because we want EDA for availability, we want it for performance, we want it for coupling, all these kind of things. And if you don't take care of it properly and you end up with head of line blocking, you actually end up in a world of pain. And I did have someone the other day tell me about how actually Kafka's great and they never had any of these problems, but then they went on to tell me about the multiple times they got woken up at 3 a.m. to deal with a head of line blocking issue. So maybe not so great for that. Let's look at message routing. Message routing is how you decide where the message actually has to go. And this is where, again, I sort of glossed over a detail before. With the queuing world, we don't just have queues, we also have topics. And if you're using Amazon, the services SNS provides you with the topics, and the SQS service provides you with the queues. If you're using Azure Service Bus, it's kind of all baked into the one service. If you're using RabbitMQ, the topic is called an exchange, and the queue is called a queue. But they all kind of, broadly speaking, play the same roles. With streams, you don't have a distinction between topics and storage. Remember I said there's topics and storage? With streams, it's just the same thing. So the topologies are actually different. And what actually happens with queues, if you're publishing an event, it goes in the topic, and then it gets copied into the queue, but with streams, it just gets written straight into the topic in Kafka. But the rest of the consumption process from the queue is exactly the same. Where it looks a bit different is where you have multiple consumers, so multiple subscribers to an event. You actually want that message to get processed twice, because maybe one of those services, the payment service, is going to handle the subscribe to the event, and when the event occurs, it's going to trigger a payment with a payment gateway, and then the other service is going to trigger some sort of a notification. So you're actually doing two different things in two different services, so you actually want the message to be processed twice. That's different to the scenario I talked about before, which was scaling out a single service, because you don't want that service to do the same thing twice. So here we're talking about two different things in two different services. And with queues, we have this concept of fan out pub sub that's actually inside the broker. The topic is explicitly linked to the queues that are going to end up processing that message. And typically the topic is related to the event, and the queues are related to the services that are going to be subscribing to that event. So you can see there's like actually a payments queue and a notifications queue. So the queues are logically connected to the purpose of the consumer, whereas the topic is connected to the event itself. So these things in the queuing world, we often call them like logical subscribers. Remember, each one of these could be represented by like 3 or 4 or 5 scaled out nodes, but as a logical subscriber, it's one thing. In the Kafka world, they call it a consumer group, because in the Kafka world, a consumer is a single node. So a collection of consumers doing the same thing is a group of consumers. The language is just kind of subtly different in these two different worlds, and I think it sort of reflects what they're focused on. In the queuing world, we focus on the logical purpose of it, and in the Kafka world, there's a lot of focus on the technical mechanisms around how it works. So in the queuing world, a consumer is a logical collection of nodes. In the Kafka world, a consumer is a single node, and this can sort of bite people if you're sort of jumping between the worlds. So if we publish an event that has 2 subscribers, in the queue world, actually 2 copies of that message get sent to those different queues. So the payments queue will get a copy of the message, and the notifications queue will get a copy of the message. But in the streams world, just 1 copy of the message is stored in that topic, because, oh, have we got a energy saving again? Is it coming back? Oh, I think, here we go. Eventually consistent systems, right? It comes back eventually. So we need 1 copy of the message, and what will happen is those 2 things will read it separately. So in the queuing world, payments will read from its queue and get the message. In the streams world, payments will read from that same topic with offset 0, and then notifications will read from that same topic with offset 0. But the notification service in the queue world is reading from a different queue. So this is how the 2 systems handle the desire when you actually do want the message to get processed twice. They have to handle it differently, because in the queuing world, if you just had 1 queue, Well, once the message is gone, it's gone, so a second service wouldn't see it. So you have to have two queues. But in the streaming world, because it's up to the client to say what offset they want, you can just store the message once and different clients can request different offsets at different times. So, but do you remember though, it's not all about events. Remember I talked about commands, like this statement of intent, and how the logical topology is that when you publish an event, it might go to multiple subscribers, but when you send a command, it's actually fanning into one handler. With the queuing world, you've kind of got topological support for that because you can bypass the topic. If you know that your shopping cart and your shipping service are sending a command to the payment service, they can just send that command directly to the queue that the payment service owns. So it kind of mirrors the logical flow of the information fanning in to the queue of that service. But with streams, because they just have the topic and the topic is the storage, you don't really have that. So you kind of have to make sure that you do something with access control lists or some other kind of convention to make sure that those commands are only getting handled by the service that is responsible for handling that command. So one of the things that this leads to is yet another irony. If you look at the Confluent documentation, they talk about a thing called a command event, because in the Kafka world, everything is a topic and things on topics are events. Then eventually you actually want to send a logical command because sometimes commands are useful, and they end up calling it a command event because reasons. So isn't it ironic? Sending a command event and I can't even finish the rhyme, it just makes no sense, WTF. Like, why would you, command event just doesn't make sense. And I found this one example of it, there's been others I've seen over the years. It's not commonly used, but you kind of see it when people are kind of just too in the weeds of the technical layer, that process view, and forgetting to come back up to the logical view and think about what's actually the purpose of these things. So anyway. Summarizing the difference between broker types. So if we're talking about the read status tracking, with queues it's handled by the broker, with streams it's handled by the consumer. If we're talking about poison message handling, with queues the broker does it for you, with streams the consumer has to do it. If we're talking about auto scaling or dynamically scaling our consumer clusters, with queues it supports totally fine, no extra work required. With streams, it does support it, but within the partition limit. It's kind of a problem if you want to scale out beyond your partition limit. You have to do some extra work to make that happen. Can you auto recover if the consumer process failures? Yes, you can with queues very easily. With streams, yes, you can-ish, but the client libraries actually do a lot of heavy lifting, and there's a complex interaction protocol with the Kafka broker, with the group coordinator, to reallocate partitions to nodes. Again, you don't really have to worry about that to make it work, but when it fails, if you don't understand what it's doing under the hood, you're gonna have a bad time trying to diagnose what's going on and working out how to resolve it. Support for semantics of commands versus events. Queues very easily, you just bypass that topic and go straight to the queue. With streams, not really, because everything's an event and a topic. This is where it goes the other way. With queues, it's up to the consumer if they want to have the historical messages recorded, because the queue is not going to do it for you. Once the message goes out of the queue, it's gone. So if you do need to keep an audit trail, or you want to keep a history of those messages, as a consumer client, it's up to you to store it. So a pretty common pattern is to create another queue, which is like an audit queue, and for every message that's successfully processed, you put a copy of it into the audit queue, and you have another process running off that pulls it out and writes it to an S3 bucket or a blob storage or a database or whatever you want for your audit storage. But it is, again, I don't want to feel like I'm just dumping on Kafka the whole time. There are things that Kafka does really well, which is the historical storage, that in a queue world you have to put extra effort into if you want it to happen. But with streams you get it for free, it's just stored in the stream. And so as a result of that, new services in the queue world cannot access those historical messages. Whereas with the stream world, they can. And this is often a justification for going with Kafka, because they're like, oh, if we think of a new service in the future, we can just spin it up and it can read the whole history of the messages and rehydrate its state from everything that's ever happened. And that sounds really great until you ever actually have to do it, because it can cause a lot of problems. And I'll talk a bit more about that in a bit. Might pause there if there's any questions, because there's a lot of stuff in that section. But that's kind of the end of the difference between queues and streams. Yep.
Buses.
Event buses.
So Amazon has event bus.
So yeah.
It into buses, but then the consumer can be SNS or a queue.
Yeah. So event buses, if you think about the kind of primitive concepts I've outlined, they're kind of just like the pure topic. They don't store the messages, so you have to set up a subscription, and it will forward it to wherever you said it should go. It's just the topic, yeah. So it's a pure routing layer. And SNS is a pure routing layer as well. Event Bridge and SNS just have different mechanisms of how they do it and different support for different kinds of things. So one of the things like SNS is more, well, I guess they both push to the destination as well. Event Bridge's got a lot of flexibility for content-based routing. So most of your subscriptions are set up based on if it matches this pattern in the payload, send it to this destination. Whereas SNS is a little bit more like just for a given topic. Yeah, for specific topics. Yeah, you have to predefine the topics, whereas Event Bridge is like just a pool of messages and you set up a rule. So it's very flexible, but functionally they're kind of doing the same thing. They're responsible for a message comes in, it decides where to send it. That's a routing responsibility, which is the responsibility of the topic. There are other systems like that as well, like MQTT is kind of just pure routing. It doesn't really store the messages as well. So if there's no storage of messages, that's like just the routing layer. To get proper pub-sub system, you need routing and storage because you have to hold the message until the consumer is ready to receive it. And you need to hold the back.
If it doesn't get consumed, it's gone.
Yeah, exactly. That's it. Does that, answer your question? Yeah, cool. Cool, but the key thing is that they're both about inter-process communication. So we're talking about, I've got some data, I want to send it to you, I'm going to use the broker to get it over there. And this is where we draw the distinction between queues and streams and event stores. Because event stores, and this has caused a lot of confusion for people who are first engaging with event-driven architecture, is because they all use the word event, right? And we just think, oh, I've got an event. It's all the same. But actually, event stores are about state. They're about state management within a service or within a bounded context. They're not about inter-process communication. So, because remember I said that you often have these pair, you've got a submit order command and then an order submitted event. There's another thing I left out here, which is this thing in the middle. We call it in the domain-driven design world an aggregate or an entity. It's the thing that actually encapsulates the business rules that decides whether or not we should allow them to submit the order. Maybe we don't allow orders that have no items in it, or we don't allow orders that are worth too much, or we don't allow to submit an order if it's got an item that's now out of stock. Whatever the business rules are that decide whether or not an order is allowed to be submitted, they live in the aggregate. And so when the command comes in, it will evaluate those rules. It needs to have all the data that it needs to have in order to decide if it should be allowed or access to that data. And then if it's all allowed, then it emits this event, order submitted. And it says, yeah, now the order has been submitted. So any other part of the system, in theory, can now proceed on the assumption that the order was fine without being aware of the details of how it got to that state of being submitted. So these events are a nice abstraction point. They later encapsulate a whole bunch of business rules and just say, here's the outcome. Don't worry about how I got there, but this is the end result. But if we're talking about event sourcing, we're actually talking about using those events as the state storage. And so this is kind of the way I think about the distinction between the pattern that most people are familiar with. So who typically just uses like NoSQL or SQL databases for their state storage? Yeah? It's like the most common thing. So using a Postgres or Microsoft SQL server, and you're creating a table per entity, and every entity in your system gets a record in that table. Or maybe using like Mongo or CouchDB or something, or Cosmos, and you're getting like a NoSQL storage, and you have the entity ID is like a JSON blob or some kind of data blob. Either way, it's about state persistence. What you're doing is you're storing the current state of the entity. Some people don't like that because you lose the record of what did the entity used to look like, and you don't know when different things happen to it unless you kind of explicitly manually track it. So a lot of people quite like event sourcing, because what event sourcing does is you don't store the current state, you just, as you decide that this event has happened, you just store that event. Some people really love event sourcing. I think it's great. I don't think necessarily everyone needs to use it all the time. It does add some complexity. You need to split the command handling, which takes in that command and decides what event needs to happen now. Separately, you also need to implement, if I assume that this event occurred, what does that mean for the current state of the system or the current state of that entity? Because what usually happens with event sourcing is when the command comes in, you need to know what the state of the entity is to evaluate the rules. And so what you do is you go and load the history of those events and replay the event accumulator effectively to get the current state so that you can evaluate the command. So this is why I describe it as that if you're doing state persistence, you store the state, and then you might publish an event to say this thing just happened. So the event is like a side effect of the state storage. But with event sourcing, you store this event and then you compute the state as a side effect of the event. So states and events, in one world, the event is the side effect, in the other world, the state is the side effect. I don't have time to really dive into like the whole story of event sourcing tonight. If you're interested in it, Hannes Levets, who's a member of the Line Breakers with Dylan, has got a lot of great talks, introductory talks on the topic, and done some podcasts about it as well. But this is kind of the key idea. The main thing to realize here is that if you're using events and you decide, oh, that means we're doing event sourcing, those events that you're putting in an event sourcing system are not necessarily the same events that you're going to want to put onto your Kafka topic or your queuing system. Because if you're doing distributed logs or streams, you're talking about a system that is optimized for give me the events for a given topic and offset greater than last offset. So it's kind of just a database. It's just optimized for this kind of query. Give me all the events on a given topic where the offset is greater than this last offset. Whereas event sourcing stores are optimized for give me all the events for a given entity ID. All right, so Kafka is not a good storage medium when what you're trying to do is event sourcing. Because as I said, with event sourcing, what you actually want to be able to get is all the events for a given entity ID. You cannot get that out of Kafka. You cannot say, just give me the events related to a given key or a given entity ID. So really want to ram this home. Because, so Kafka has stream per topic. Event stores have a stream per entity instance. Why would anyone think that Kafka is a good storage medium for event sourcing? Maybe because in 2017, Confluent published this article talking about event sourcing in the context of Kafka, and it went through this whole thing about how great it is to use Kafka to store your events because it's an event storing mechanism. When you actually dig into what they're talking about here, they kind of bypass the whole question of retrieving the events per entity, because what they did is they said, well, we will put another system here that's constantly consuming the events and keeping a separate up-to-date copy of the state stored at all times. Which is fine, you can do that if you want to, but you should be aware that you're kind of locked into that pattern. Some people that do event sourcing do that as well, even if they're not using Kafka, but you've got the flexibility, you don't have to do that. So, thank you, Alanis. One more irony, it's an event streaming log when your state's out of date, because it's just not the thing. Don't use Kafka and think that you're doing event sourcing. Thankfully, later they did improve this. They had other articles, 2023, I think this was, what is event sourcing? And they went in and said, it's a mistake to assume that every event stored in an event source system is also emitted to Kafka. So they kind of owned up to their error. Unfortunately, a lot of people were sort of harmed by this, I think, up until this point. But then they started to talk about this difference between domain events and integration events, and I think this is a shame. They're not the only ones that make this mistake, by the way. Microsoft also has articles that talks about the difference between domain events and integration events, and I think they're all wrong. I think this is a big error of thinking and a bit of a problem, because let's go back to that event storm, which remember is in the logical view. We're just talking about the business domain here and the things that happen in your business. And remember, we broke it up into bounded contexts, and we said these things are responsible for different parts of the business process. And then I said, well, at some point, some events from the shopping cart need to get communicated to the payments context to trigger the next step in the workflow in the downstream system. So we can actually kind of shift the way we represent this and put some of those events on the boundary. And the way I think about this is that if there's domain events that are inside the bounded context that you don't want other contexts to know about, we call them private domain events. And those events that are on the boundary that actually flow through to other bounded contexts, we can call them public domain events, because they're all domain events. When we did the event storm, they were all domain events. We didn't know at that point which was going to be inside the boundary and which was going to cross the boundaries. Eventually we worked out some of them are private and some of them are public. And I kind of prefer that terminology because it also relates to what we're familiar with from object-oriented programming. Some of your fields are public, some of them are private. So you know that public means it's a contract. It means other consumers might be reading from it. Private is just owned by the encapsulated system. You're much more free to evolve it and change it without worrying about other people messing with it. And this is kind of the whole thing about information hiding and encapsulation that we've been striving for in systems design for decades. So let's get into some guidelines when we have this event. Where does it actually go? So private domain events. So we're talking about an event here that happens within a bounded context. We're pretty confident no other bounded context needs to know about it, but it actually represents the data. So I've put here if there's an ID and then lots of data. Because remember, if we're doing event sourcing, the events are the state. They have to have the data on them. So this is, if we're talking about using events as the source of truth or the historical record, and just a reminder, you don't have to do this. State persistence is still a very reasonable, effective mechanism. But if you're in a world where having the history of events is very useful, or you're quite comfortable with thinking about how to implement logic as a mixture of command handlers and event processes, then this can work really well. So event sourcing with a dedicated event store is the right way to do it. So when I talk about a dedicated event store, in the .NET world, Marten is a great example of that. So it actually wraps PostgreSQL, and it stores your events in a PostgreSQL table, but it gives you a whole bunch of wrappers around it that makes it very easy to use. And it lets you think about the world and model your business logic into these kind of things. If you're talking about something where you actually want to trigger the next step in an internal workflow, so something that's the next step in a business process that happens within a bounded context, well, every event is critical. Like you definitely need the next thing to happen, right? So I think the best technology for this is a queue-based pub subsystem, because we just saw how they are oriented by default to make it very easy to ensure that every message eventually gets processed. The interesting thing about this is that you might have stored that event into an event store, and then there'll be, like, most event stores have some kind of subscription mechanism that allows you to register a callback handler when it detects a new event, and then that callback handler can push it out onto the queue. I don't recommend doing a lot of complex business logic in that callback handler, because it's a little more complex in terms of the transaction scope, and if it fails, what happens, and you can actually end up with head-of-line blocking in that situation as well. So just do a very simple mapping onto a public or a message that's going to go into your queuing system, and then subscribe to it within the same bounded context. So the key thing here is that the producer and consumer, they might be different runtime nodes, they might even be the same node, but critically, in the logical view, they belong to the same bounded context. So just because a message is going onto a queue doesn't mean it's a public message. You can actually put private messages on the queues as long as the only thing that's subscribing to it is that same logical boundary, that same bounded context. If we're talking about events and we want to use them for things like Internet of Things or click streams or anomaly detection or moving average threshold crossing or statistical aggregation over time, what we're kind of talking about here is situations where the individual events are less important than the stream of the events, right? We're talking about averages and aggregates over time. This is what distributed logs were built for. Like, they actually evolved, I think it was in LinkedIn, for handling like click streams and click stream analytics, and they're looking at like aggregates and reporting over the whole user base. If a single one gets lost, like, who cares, right? We're just looking at that thing over time. And again, if you are doing it within a bounded context, the producer and consumer can belong to the same bounded context. Doesn't mean it needs to be a public event that you need to manage as a contract. But if you are doing this, I also strongly recommend looking at these other systems like KSQLDB and Flink. They are optimized for plugging onto a Kafka topic and converting that into some sort of reporting. You can write queries that very easily will sort of produce new data streams based on like moving averages over the last 1 hour or the last 1 day, all this kind of stuff. And that's kind of what they're for. So use the right tool for the job. And then that can either emit new events into a new topic that represent like summaries and roll-ups and aggregates or whatever, or like hydrate it into a static state storage for whatever reason. If that's what you need to do, don't use a queue, because you're going to be re-implementing a lot of that yourself. So this is actually the right technology for streaming. So that was all public events. Sorry, that was all private events. Let's talk about public events, those ones that sit on the boundary. One of the things I like to encourage people to do with public events is really slim them down. Go to like really lightweight, small contracts, because the more data you put into a public contract, the more risk that at some point in the future you're going to have to modify your system in a way that changes the contract, and then all of your downstream subscribers are going to have to be modified to absorb that potentially. The less data you put on there, the less risk. And the less data you put on there, the better job it indicates that you've done of actually encapsulating a business process and the associated data with it. Not saying that this is like the only way to do it. Sometimes you do need to share data between systems. I strongly encourage you to only do that in cases where the data itself is immutable, so it's not going to change later, because once it escapes that boundary, controlling the sequencing of updates to it, it gets a little bit more tricky. And when the schema is quite stable. So I had a situation once where I made a terrible mistake here. We put a date time onto this thing, and then it turned out later we probably should have put a date time with a time zone. And we had like 5 subscribers to that event, and that was a huge pain in the ass to go and update everybody to start worrying about time zones. We realized later that there was a better system design that would have actually encapsulated that data, and those other systems didn't even need to know about that date time. So, or the fact that it had a time zone. So this is really about encapsulating future changes that you might need to make and thinking about trying to design those contracts in a way that's stable into the future. Sometimes you see people worried about this, and this term evolved. I actually quite like the term. Oscar Dudic, who's really big in the event-driven architecture community, proposed this a while ago, called a clickbait event. And I think that what I'm talking about here is not a clickbait event. What Oscar calls a clickbait event is when you publish an event that just has an ID on it, but the downstream service actually does need more data. And so what it does is it calls back into the service on an API to get the data. So that's what it means, like a clickbait event. It's like a headline going, oh, something's happened. But then you actually have to read it to find out. You've got to go back and call back into the data to get it. And so this might fool you into thinking that you've created a more loosely coupled system with like a nice contract that's not going to change and not going to cause like change propagation and change contagion across your system. But actually, because you've just shifted it into the API, you've still got that exact same problem. If the domain changes, you're going to be updating your domain models, you're going to actually update the API, you're going to have to coordinate changes with the downstream consumers so that they can read that new API call. So this is a terrible idea. Don't do this. This is what Oscar called a clickbait event, and I agree it's a terrible idea. The way to actually solve this problem, I think, is to go back to your event storm and realize, well, we actually missed something here. We never captured explicitly how do we know where to ship the order, right? So let's make a bit of space here and say, well, we also need to have entered the shipping address, and now we have an event, the shipping address is set. But then that makes you realize, like, why is the shopping cart capturing the shipping address? It's not actually got, if the purpose of the shopping cart bounded context is to keep track of the items in the cart, why is it also capturing the shipping address? And what you can do is you can split it in the business process and actually have the shipping service take care of that at the time of constructing the shopping cart. Some people get like really confused by this, but you don't, the bounded contexts don't have to be contiguous in the flow of the information. You can have the shopping cart do some things, the shipping service can do some things, and the shopping cart can handle the submission order. And then by the time the event flows through to shipping and it says, oh, you ready for me to ship it? I've already got the address. I know what it is. And so if something comes along later and says, well, we built the first version of our shipping service and the only thing that we offer is, what's your postal service again? Yep. His Majesty's Royal Postal Service, Royal Mail. We only support Royal Mail, and then later on they go, oh, we're going to America, now we need to support FedEx as well. Well, the team that owns the shipping service can take care of that whole change for you without coordinating with any other teams. So this is a very nice pattern to adopt if you can do this. It does have some extra complexity in the UI, which is another talk if we get into that. But the value of this now is that your event can actually just be the ID, because the shipping service already has all the data it needs. It doesn't have to call back into the shopping cart service. It doesn't need to know the items in it. It just needs to know where to send it. So this again is an example of encapsulation. Have we actually put the data and the logic in the place that the logic works with the data it needs, and we're not just like copying data all over the place just because we put it in the wrong spot and we don't know what to do with it. So this is the thing that can help you think about that kind of thing, because the data is already where it needs to be. In the shipping service, we've got the list of items, and in the shopping cart, in the shipping service, we've got the shipping address, and in the database, we've got a list of items. And this is a true distributed system. You've got your entity is decomposed and split across your system. Have you ever worked in an environment where you've got like an orders service, and the orders service knows everything about the order? It's probably a very tightly coupled environment, because every service is going to be calling that service to get the data. And what you've really done is you've just created a database wrapped in some software, and you've made that a centralized component of your system, and all your other services are reading from that same database, which is something that we said we weren't going to do when we did microservices, right? So this actually works if you do it this way. So public domain events. If we're talking about allowing the subscriber bounding context to react and execute the next steps in business process workflows, every event is critical. Queue-based pub sub, it just works. It does it for you. If the events fail, they go to the dead letter queue. You can make sure that they eventually get processed. In this case, the producer and consumer are usually different bounded contexts, and that's what you expect. So this becomes a public message because it's going between two different logical boundaries of ownership. Then we've got this kind of thing where we go, well, it's a public event, but sometimes we actually do need a lot of data on it. Like maybe we have a customer context and we're saying customer address updated, and we're putting a whole bunch of data on it because other services, they just need to know the customer address. So I put a question mark next to the word domain event here because it's very rarely the case that a business domain expert will put an orange sticky note on the wall saying record updated, right? It's not a domain event. It actually is, I think, an integration event, because the only reason we've created this event is to share data because we made a choice about how to decompose our system and we needed to get the data from one place to another. It fulfills a technical purpose. It's not a domain event. It doesn't represent a thing that is meaningful in the domain. It represents a piece of technical functionality we need to implement because of how we designed the system. So I think this is actually the right place to use the term integration event, because you're talking about integrating two systems for the purposes of sharing data, not because it actually represents a meaningful concept from the domain. Often this kind of thing, when you see a big event with lots of data on it that's getting emitted every time anything is modified, it's an example of what's called event carried state transfer, when we're actually saying the whole state of the entity is being transferred to another system and we're just carrying that state on an event. Really try to avoid this if you can. Like, there are legacy systems when you're starting to do EDA in a legacy system where you probably need to do this for a while. But if you're designing a system from scratch, you can usually get away without doing this, and because this is just like, if I said that like having lots of data on your events increases the risk that you're going to have downstream change propagation, this is like the sort of ground zero of that kind of phenomenon. And like out of order message processing, all that kind of stuff. Often in this case, the individual events may not matter because it doesn't represent a meaningful concept from the domain. It's just updating data. So if you drop one, the next event will have a more up-to-date record anyway. I mean, it's not going to mean that a thing doesn't happen that needs to happen. It might mean that there's a delay on the data being up to date. But you know, your mileage may vary on how important that is. But streaming systems are actually really good at this. Especially using something like Kafka Connect, which is another system that's built to hook into Kafka, and it's specifically designed for routing those messages or transforming them in some way. And so this is actually something Ian Cooper calls forward cache. So who knows Ian? Probably a lot of people, right? Because he's one of the coordinators of the group. One of the co-founders, I think, right back when.
The founder.
The founder, the OG, yeah. So I've had some conversations with him and he calls this thing a forward cache, because what he's really talking about is like, okay, yes, in an ideal world, my downstream servers wouldn't need this data, but it actually often does. And I don't want to create the load on my primary system of calling back into the API all the time. So I'm going to pre-populate a forward cache so that it can just get accessed quite easily from the downstream service. And managing it as a contract means that yes, if the thing changes inside the producer, like I'm going to have to update the downstream eventually, but I don't have to do it at the same time because I can just maintain that contract, which is like a DTO on an API, right? You do that to sort of decouple it from internal changes. But if this is what you need to do, and again, I think it's better if you don't need to do it, but sometimes you do, this is the way to do that. This is kind of like what was the point of this? So it breaks encapsulation, right? Because what you're really saying is we've got a service that owns the data, but we're reading from that data. Even though we're reading, it still breaks encapsulation. With private topics, it's the same thing. So with databases, everyone, if I go back to this slide, everyone knows this is a bad idea, right? Who would look at this and say, yeah, this is a good design? I'm going to have a private database, but I'm going to like sneakily let other services read from that database, right? Like I think we know by now as an industry we shouldn't do this. Doesn't mean we don't, lots of places do, but we know we shouldn't because it breaks encapsulation. It means that the team is going to maybe modify that schema of that database and just silently cause downstream services to fail. And that's the whole reason microservices started pushing people towards API-based communication rather than direct database access. But if you have a topic and you intended that topic to be private, and you say, well, I intended for my that same service to subscribe to it because I wanted to do some data aggregation or I wanted to trigger a private workflow, you're doing the same thing. Like when I draw it this way, it's obvious that it's the same pattern. So it breaks encapsulation if your intent was for that event to be private. And I've worked with clients who just went, oh, we're putting all this data in Kafka. Kafka is like a centralized broker. So now Kafka is the source of truth and everything should just get everything they need from Kafka. And they don't realize that what they've just done is they've gone back to the old world of having one centralized database that all the services are reading and writing from. So if you care about encapsulation, if you care about the autonomy of your services, don't do this. But it does raise the question, because when you just look at the broker, you've got all these topics, or you look at your queuing system, you've got all these queues and topics and exchanges or whatever. Like, it can be hard to tell some of them are public and some of them are private. Like with just pure database and APIs, it's obvious. The API is public and the stuff in the database is private. But when these things are shared on a broker, it's a little bit trickier. So how do you actually ensure that you sort of don't break encapsulation? So the simplest way is, if you're using the same language in all your services, just like use the language features. Create like a dedicated in .NET assembly for your contracts, and put your public events into your contracts assembly, and put your private events into your main application, and publish the contracts assembly, maybe via a private NuGet or maybe some other monorepo mechanism, whatever it is, but just make sure that your other services only take a dependency on your contracts assembly and not on your other assemblies. And that means that now you can know what they've got visibility of and what you need to manage in a careful way when it comes to changing them. Another way to do it, if you don't have the same like homogeneous environment, maybe you've got some services in .NET and some in Go, things like async API are becoming very common mechanisms. It's like the Swagger or Open API equivalent for async world. Just put the public ones in your async API and keep the private ones not in your async API, because your private ones shouldn't be getting read by other services anyway. So the async API should only represent your public surface area of your events. Who's familiar with Event Catalog? Has anyone come across this tool? It's created by a guy called Dave Boyne. I think he's in Manchester, actually. You know Dave? Is it Manchester? I think it's Manchester.
He was AWS, but
He was AWS. He's independent now.
I just bumped into him.
Yeah, he does a lot of NDC events. He's built this tool called Event Catalog. It started out open source and he's gone commercial with it. He's doing really well. But it's a great tool for documenting event-driven architectures, and it lets you suck in data from schema registries and other systems and write sort of documentation into Markdown files, and it just sort of publishes a really great documentation resource for all your different components and systems and events, and visualize the flow of events through your system. So I recommend checking it out. He doesn't yet have like explicit support for public and private indicators, but he told me he's adding that soon. So keep an eye on that, and they'll help you keep track of what's public and what's private. So a bit of a summary of our heuristics. If you're talking about private events that are about state management, put them in an event store like Martin, and just don't let them be public, at least not by default. If you are going to make them public, copy them to a dedicated DTO event, so you can manage that contract independently of your domain events. And that's what we talk about business process, which might be public or private, but we're talking about queue-based pub sub, because we want to take advantage of those mechanisms that give you very helpful handling of failed messages and retries, and just making sure every message eventually gets processed. If we're talking about streaming analytics, like time series windows and producing new streams based on things that happen, use a distributed log and use those systems like Flink to help you do that, because that's what they're designed for. If we're talking about forward caching, distributed log, but that should really be treated only for public events and public caches, because we're explicitly saying we want other bounded contexts to consume that data. So that's not something you would think about doing in the world of a private system. So this kind of summarizes my heuristics. These are not hard and fast rules. And again, I'm not saying you can't, apart from the event store, I think there's a clear boundary between event stores and queues and streams. If you're using queues, you can do pretty much everything that you would want to do with the streaming system. You just have to put more effort into some of those things. If you're using streaming system, you can do pretty much everything you want to do with a queue, but you're going to have to put more effort and be aware of what's going on under the hood for some of those things. So these heuristics that I like are there because they guide you towards what those tools are like default good at, what their native capabilities are. So make sure this is not the good advice that you just didn't take, and listen to what I had to say here tonight. Thank you, Alanis, for your help. If you want to see some code examples, and if we've got time I can show you briefly, but I've actually prepared some C# code that illustrates all of those scenarios that I went through, and it does it for RabbitMQ and Kafka as a low-level consumer and as a high-level consumer. So you can see the different behaviors between them, and it's written with a bunch of unit tests that will show you like the actual behavior that you would expect to see from the different types of brokers. So if you're curious to check that out, that's all there. I think it's all in here. So you can see it's like consumer scale out, and then there's like different scenarios, one handler fails, scaling out past the partition count with the partitions, etc. And for each one, it's done with the parameterized high-level Kafka, low-level Kafka, and RabbitMQ. So you can see all these different tests, groups and different scenarios within it. And yeah, hopefully that's helpful if you're still trying to understand what I've been talking about tonight. I have a training course that a lot of this material is drawn from. It's called Imagine the Future and Build for the Now. Some people told me they think it's a really catchy title. Some people have told me they think I'm a complete wanker for coming up with this title. So I'll let you be the judge. But I'm running this with DDD Academy later this year. Unfortunately, it's in an Australian-friendly time zone, which is not that great for the UK. But I am happy to have conversations about private runnings of this course or finding other public editions at different time zones if there's enough interest. The stuff that we talked about today is from this module called Interprocess Communication. The rest of the courses really leans heavily on that 4+1 views, so we learn a lot about how to think about systems from different perspectives and how to think about mapping the system perspective between the different perspectives, and a lot of it is like, how do you represent in the developer view to make sure that you've got a clean alignment with what's actually going on into your runtime, but also critically your logical view. So we actually do some event storming. I've started to integrate Barry O'Reilly's residuality theory, which is another really interesting topic that we haven't got enough time to talk about tonight. And yeah, it's a 2-day course. So have a chat with me later if that's of interest. Otherwise, thank you very much for your attention. And yeah, look forward to conversations later.